This video is to help you complete your circles foldable. So in class we had it all folded, and so now I'm going to help you fill it out. Okay, so if you open up the first page, we're just going to look at central angles. We've talked about that. So central angles, you know that angle 1, the measure of it, is congruent to or equal to the measure of the arc, the intercepted arc here. Okay, now the next thing we talked about were inscribed angles, and so I'm going to flip it around this way and open it up. So when we're talking about the family of inscribed angles, we have noticed that inscribed angles, the vertex for each one of these is on the circle itself. Now here all the vertices are on the circle itself, but this is actually forming a quadrilateral. So we're going to talk about it in a second. But here we've got these two inscribed angles. Now they look very different because this one, both chords that make it up lie inside the circle. However, this one has one inside and one outside. That doesn't matter because the angle itself falls inside the circle. So what you're doing is exactly the same formula for each one. The measure of angle 1 is 1/2 the intercepted arc. Here, the measure of angle 1 is 1/2 the intercepted arc. Now over here, we still have these inscribed angles, but in this case, they form a quadrilateral. So what you know, in addition to these things, is that the opposite angles of the quadrilateral are supplementary. So D plus B is 180, A plus C equals 180. Okay, so now I'm going to fold that back in and look at chords. So this is going back to the front of our booklet. Here it is. Here's central angles, and now here is chords. So if we have chords that intersect in a circle, the product of the two parts are equal to each other, so they make a ratio. So W times X, that product, is equal to Y times Z. All right, now if we fold that and then look at right angles. So there's two cases here that I want you to consider. One is here. Notice that AD is the diameter, and so I've drawn in AED. No matter where I put E on this half of the circle, I know that it's going to be a right angle. And when you think about it, this is actually an inscribed angle. And the amount of the measure here, because this is a diameter, is 180. So half of 180 is 90. So that's why that works. Now here we have another situation where I could extend this out to say, like the theorem does, that this is a diameter. Okay? So here this orange chord is a diameter. Notice that the diameter is perpendicular to this chord. If that ever happens, if the diameter is perpendicular to the chord, then we know that it bisects the chord. So AB is congruent to BC. Also, you can use the converse of this. If a chord in the circle bisects a chord like this and is perpendicular to it, you know it's the diameter. Okay? Now, if we fold open to the very center, we have what we call the family of secants. So the family of secants, notice that all of the vertices for each one of our angles is outside the circle. Notice that there are two arcs that are formed when it intersects the circle. So we have what I'm going to call the big arc for each one of these. Okay, the outside one, the big arc. And we also have the little arc, the one that's inside and closer to the angle. All right, now for all of these, the equation is exactly the same. The measure of this angle 1 is equal to 1/2 the difference of the big arc and the little arc. Okay, so here we would write the same thing. Even though it looks a little different, we have a tangent and a secant, it's still going to be the same thing. So still the measure of angle 1 is going to equal 1/2 the measure of arc B the difference of B and A. Now I realize this isn't really good notation. I'm just trying to get you to remember the formulas that you're using. And here, even though we have two tangents, it turns out is still exactly the same formula. Okay, so if your angle's outside the circle like this, you have tangents or secants, it's the same formula all the way across. Now, the other thing that we know here is that we've got a relationship with the lengths here. So I know here that the length of y times the whole length, so y plus z, equals w times w plus z, w plus x, excuse me. Here, it's going to be the same thing. Y times y plus z, the whole chord, equals w times the whole chord, which is, again, w, so w squared. Okay? For this one, we've got y times the whole, so we're doing the whole thing. The outside part times the whole, so y times y equals w times w. Now, this would be y squared equals w squared, but we could easily take the square root of both and really just shorten it to be y equals w. So we know if we have a point outside the circle that is has tangencies to the circle, we know that that length is the same from the point to the circle, to that point of tangency. Now, the rest of the inside here is the equation of a circle, and remember we corrected this here, so your center is always known as HK, and the point on the circle is actually XY. Okay, so here's your equation. The center of the circle is denoted by HK, and R is the radius. Now notice that the radius is squared. This is very similar to the distance formula. Circumference of a circle, circumference equals 2 times pi times r, or pi d. This is the preferred because moving forward in math, you're often given the radius and not the diameter. You just tend to use it more. Here, if we have arc length, we're talking about if I want to know how far it is from here to here. So if I'm looking at this, I see that it's just a portion of my entire circumference. My entire circumference is whatever this angle is, theta over 360. That's the portion that it is, times the circumference. So this is the portion of the whole circumference. The area of a circle, I know, is pi r squared. If I want to know the area of this sector, so just this little portion, I need to find out what portion of the circle do I have. So I have theta out of 360 degrees, so this would be my portion. So if this were a 90-degree angle, it would be 1/4 because it would be 90 over 360. And then it's a portion of my area. Okay, and that completes your circle foldable.